Lecture number 75. We are studying transient analysis of circuits, and in our last lecture, we studied expressions for IC, the current, voltage drop across resistor, and for voltage drop across capacitor for a series RC circuit excited with a DC input source in the presence of a switch K that was closed at time t is equal to 0. We calculated expressions for the current in the circuit and the voltage drop across the two elements, resistor and capacitor, for all values of t using differential equation approach. In this lecture, we will continue studying transient analysis and we'll take on this circuit. This is a series RL circuit in the presence of a switch K, which is closed at time t is equal to 0. Before that, the switch was open and there was no current in the series circuit. So switch K is closed at time t is equal to 0. What happens just after we have closed the switch? Time t is equal to 0 plus. We already know that this inductor becomes short circuit because the current through it cannot change all of a sudden, because the expression for current we studied a couple of lectures before. It involves an integral term. Therefore, it cannot change all of a sudden, minus infinity to t v sub L of t. So this term involves an integral. Therefore, current cannot change all of a sudden in an inductor, and just after we close the switch, there is no current in the loop. Therefore, it is 0 at time t is equal to 0 plus, but it doesn't remain 0 for all t. It starts increasing and finally becomes equal to v over r, because finally it gets short circuited as time approaches infinity. As the time approaches infinity, this inductor becomes short circuited and the current is then v over r. But as soon as we close the switch, it is open circuited because current through it cannot change all of a sudden, and the current through it at time t is equal to 0 minus was 0, so it remains 0 even at time t is equal to 0 plus. Since there is no current in the circuit, the voltage drop across R is 0, because for our voltage drop across R, there must be a current flowing. Only then we can have a voltage drop across resistor. And then VL at 0 plus this voltage, the voltage drop across inductor, is the same as the applied voltage. What happens at time t is equal to infinity? The current through this inductor is initially 0, but then it starts building up, and finally inductor is short circuited as time approaches infinity. So this is the inductor replaced with a short circuit. What is the current then at time t is equal to infinity? V over r, because it is short circuited. So the only elements in the circuit are V and this R, so the current has to be V over R. Voltage drop across inductor at time t is equal to infinity is 0, because it is replaced with a short circuit, whereas voltage drop across resistor is the same as the applied voltage, because this is the only element across which we can have a voltage drop. Right, so now it is the time to compute expressions for I, V, VL and VR for all t. For that, we have to write just as we did for the RC circuit in last couple of lectures. In fact, we'll write a KVL equation for the series circuit: minus V plus R times I sub L of t plus we know that the voltage drop V is L times the time derivative of I. We have already studied that the voltage drop across inductor is the inductance times the time derivative of the current flowing through it. So since this is a series circuit and there is only one current, we call it I sub L of t. Right? We can rearrange terms by dividing this whole equation by this L, capital L, then it becomes this differential equation. And we know, we studied in last couple of lectures, that for these kind of differential first order differential equations where we have a constant term here on the right hand side, it's not function of time. For these equations we have this general solution, the particular solution and the complementary solution. And the particular solution is a constant and complementary solution is k2 times e to the minus t over tau. So now to compute this I sub L of t, we need to find three variables, the values of three constants, k1, k2, and tau. We studied when we were analyzing RC circuits, we studied that we can find two of these unknowns by putting initial conditions. We know at time t is equal to 0, what is I? We computed that I was 0. At time t is equal to 0 plus I is 0. So let's put I is equal to 0. Sorry, t is equal to 0. So IL of 0 is equal to k1 plus k2 e to the minus. Put this t is equal to 0. We know that e to the minus 0 is a 0 because e to the minus 0 is 1 over e to the 0, and e to the 0, anything raised to the power 0 is a 1, so it becomes 1 over 1. This means it's a 1, so it's a 1, so it becomes k1 plus k2, and the IL of 0 is also a 0. So k2 is minus k1 or k1 is minus k2, or their sum is 0. At time t is equal to infinity, we have already studied that for that we have this current V over R because the inductor is short circuited, and we have V over R current flowing as the time approaches infinity. So IL at infinity is V over R, and we put T in the whole equation, in this equation number 2, k1 plus k2 e to the minus infinity over t. And we know that e to the minus infinity is a 0. Why? Because e to the minus infinity is 1 over e to the infinity, and e to the infinity, anything raised to the power infinity, provided the value is greater than 1, it is infinity, and 1 over infinity is a 0. So k1 is V over R. If k1 is V over R, k2 is minus k1. This is minus V over R. Now we have computed two unknowns, k1 and k2, and the only unknown is then tau. For that we have to put this equation in equation number 1. What is equation number 1? This one, the initial equation that we computed, that we wrote using KVL, by applying KVL. So putting this in equation number 1 gives us this much, and if we solve this tau becomes L over R. So IL of t is this, or we can write it like this. In our next lectures we will plot IL of t, we'll compute V sub R of t, V sub L of t, and we'll plot all these quantities. Thank you.